All right, thank you so much for the warm introduction, and thank you for inviting me here at EPFL. I always wanted to visit Switzerland, and there are a lot of interesting research here. So I will get started with my talk today on generative models for biomolecular design. I'm pretty sure this is a very hot topic. There's a lot of protein design folks here at EPFL, so I'm sure that some of these work will be interest to you. So yeah, just to briefly introduce, like AI has been revolutionizing, biomolecular design. There has been a lot of exciting applications in drug discovery, protein structure prediction, protein design. I'm sure some of you already know. Some of my earlier work on application of graph neural networks has made a lot of success in drug discovery, especially in the world of antibiotic discovery. This is one of the papers that we first published in Cell back in 2020 during the COVID time, where we discovered a new antibiotic that can kill multi-drug resistant bacteria in that is validated in mice. And there has been, more recently, there has been a lot of success of AI models for protein design. There's the RF diffusion paper from University of Washington, from David Baker's lab. There's also BindCraft from EPFL, from Bruno's lab. These are all making exciting progress in designing binders with protein binders with generated models. So this is a very exciting field, and there are many things going on. And just for those who are not familiar with this problem, I just want to give sort of one slide or introduction of what we care about, right? So basically we want to design molecules with some sort of desired properties, right? So by properties, they actually mean many. It could be many things, right? In the case of antibiotics, we could care about like antibacterial activities, whether a molecule can kill the bacteria, or it could be antiviral, anti-cancer, you just name it. In the case of protein design or small molecule too, you also sometimes care about whether it can bind to a given target or protein. You also care about these toxicity or other physiochemical properties of a molecule. Right, and by molecules or biomolecules, I do mean a variety of things, like small molecules, which is particularly used for drugs. Small molecule drugs is quite common in pharmaceutical industry, but there's also biologics like proteins or nucleic acids that we'd like to design. Right, so in my view, of course, this is a relatively high level description of the biomolecular design sort of system. It typically involves like three components: the generating model that can generate biomolecules with desired properties, and you have a scoring model that tries to evaluate whether a designed molecule satisfies your constraint, and of course you need an experimental platform to validate whether your designed molecule works. Right? That's kind of a high-level summary of a biomolecular design system. Right, and of course, each of the components have, there are many challenges that involves that for each of the components, and these challenges motivate new algorithmic innovation, and I will talk about some of those today. Of course, the field is very. If you go to a machine learning conference, there are a lot of papers try to tackle different type of develop different type of models to tackle different facets of challenges in any of these components, right? So I will only be able to talk about some of them. So we'll talk about the challenge of generating complex geometric objects in the context of small molecule, and we'll, in the second part of my talk today, we'll talk about how to learn a binding or energy-based model to quantify binding energy in a unsupervised way, and we'll also talk about how to integrate all these machine learning models with a physical lab to build a fully autonomous design system, right? So that you can actually do a closed loop design, right, with multiple iterations. So yeah, we'll start my talk with the first component, how to generate complex geometric objects, particularly graphs, and how to apply that to design new antibiotics. This is kind of a follow-up work that we have recently published in Cell in actually last week. So which we applied generative models that I developed several years ago and successfully designed new antibiotics, validated in mice. It took several years to do this. So just for those who are not familiar with antibiotics, why do we care about antibiotics? That's because antibiotic resistance is a big problem right now. If you look at this figure on the left, the death rate from these drug-resistant infections is actually skyrocketing, and the CDC estimated by the year of 2050, the death rate will actually match cancer, right? And have to say that several I hear some of my friends, their grandparents passing away, they don't die of their cancer or whatever, they die of pneumonia at the end because of these resistant bacteria. So this is a really nasty thing that we really should do something about it, right? And you can see on the right, there's a list of high priority bugs that CDC want people to really find solutions, right? And there's been actually Gates Foundation is asking for grant proposals, it is really a important problem that I think many people are, is neglected by the industry because there's not much revenue that you can get out of it. That's why it's really a perfect scenario for academia to do something, right? And what's more interesting is since the discovery of the first antibiotic, which is the penicillin back in the 1920s, of course we made in the last century we made pretty big progress. Different classes of antibiotics have been discovered, but after a while, in the past 2 or 3 decades, there has been iterations of the improvement of these antibiotic classes, but nothing really, there's no really fundamentally new class of antibiotic being discovered. And the reason why this is the case has to be that the complexity of the chemical space, right? So if you think about the chemical space like this pile of heap, right? I don't know if this is a perfect analogy, but it's like finding a needle in a haystack, right? And if you if you're familiar with what pharmaceutical industry typically do, they typically just run screening, right? These robots, they can scan hundreds of thousands of molecules and measure their properties and trying to find some which we call hits, right? Some molecules that display the properties of interest, right? But this thing is only feasible in industry. It's not really feasible in an academic lab. It takes about $1 million to run this, and it takes a long time to do this, right? And what's more is, at the end of the day, these expensive robots, they can only scan through millions of compounds. But if you compare to this enormous chemical space, which many people have different estimates, 10 to the 60th or beyond. We don't know what's the exact theoretical space, but if compared to this astronomous number, what experimental screen can capture is only a small dot compared to this big heap, right? So you put so much money, but you could only scan through a tiny bit of the space, right? So we'd like to try to go beyond this experimental screening, which is laborious and also time-consuming, right? We want to design something that's more intelligent, and so that's where the generative model comes in, where you could try to basically follow the generate, score, and test sort of loop, right? So here we only showed the generation and the prediction part, right? Basically, try to map all these molecules, the chemical space into this landscape where you can map all the molecules to this property landscape, and then you can try to search in this structure activity kind of functional function and try to find the molecule with the best property, right? So the key is to how to build this generative model and also the the property prediction model, which can evaluate the molecules that you design. Right? I hope this loop is kind of straightforward. So we'll talk about. I will start with the general kind of framework and then go through the methodological details. So let's look at the property predictors, right? In this case, we did a small-scale experimental screen through collaboration with people at the Broad, the Collins lab at the Broad. And we basically screened about 40,000 molecules, measured whether they measured their phenotype, whether it can inhibit the growth of the bacteria, right? So, and we we did 2 replicates, and we found that the quality of the data set is generated data is good, and we binderized it, right? So we had around 500 actives that are that has low high growth inhibition, and the rest as inactive, right? And we basically put them together into this nice data set. We also did similar thing to measure the toxicity of each compound, because you don't want something that's toxic, right? You want to kill the bacteria selectively. We don't want to die before the bacteria dies. Okay, so of course we did a similar thing, but we, instead of the screening the bacteria, we screened the human cells, right? We measured their viability when upon the drug perturbation, and we similarly collected. We did 2 replicates, and we looked at binderized it, and we curated this data set, right? And basically, we after the data set is curated, we trained this graph neural network model, which is very standard now, right? When back in the days when I was a PhD, this is a very sort of a dynamic area where there, of course, even now there's still a lot of new methods being developed. And we choose some off-the-shelf graph neural network here, which we developed 3 years ago. About 5 years ago already. We trained a model to predict, whether basically use graph neural network to encode each molecular structure and learn to do this classification task of distinguishing these antibacterial molecules from non-antibacterial molecules, right? We also trained similar model for the toxicity, right? And we basically built 2 models, one for predicting the antibacterial activity, one for the toxicity, right? And then we can use both models to evaluate how good a new molecule would be, right? We basically we showed that we plotted the AUPRC, the precision recall curve, and we found that we basically did extensive hyperparameter tuning and with model ensembles, and get the best model as we can using based on graph neural network. And we had basically 2 predictors, one for the toxicity, one for the antibacterial activity. So that's about the property predictor, which I will not dive deep into the model architecture today. For the generated model, I will talk a bit more detail about how we generate a chemical structure. This is a model that we developed a while back called junction tree variational autoencoder, but we applied more recently to this generative antibiotic design problem. And we did more modification to the original JT-VAE framework so that it can do both lead optimization, where if you have a hit from your experimental screen, can you optimize it to improve its activity. We also try, of course, we can also do this for purely de novo design, where you just ask the model to generate a molecule that can kill the bacteria, but not toxic, right? So we basically modify the JT-VAE framework, which to tackle both problems, both settings. So let me go through the results first, because I want to show that first how well this thing works, and then we can dive deep a bit more detail how this methodology works, right? So let's talk about the 2 settings, right? As I mentioned, first the lead optimization, right? So from the initial screen that we did across the 40,000-ish molecules, right? There are like about 500 hits. The best hit, we took the best 2 hits, right? These are the two best hits that we found through the experimental screen, and we did find, it has decent activity, right? The potency is around 16 microgram milliliter, right? But the selectivity wasn't that great, right? So you can, with the same potency that kills the bacteria, it's almost about being toxic, right? If you just double it, you will start to become toxic, right? So the selectivity is defined by the toxicity, whether you can basically the concentration that you can kill the human cells versus the concentration that you can kill the bacteria, right? So we want this to be as selective as possible, right? So clearly, the initial hits that we found through the experimental screen, which is already kind of expensive, but we can't get the good result out of it, right? So so we showed using this generated model, which we'll describe the method in several slides later. We can learn to do this lead optimization by keeping one of the pharmacophore, because these two molecules share the same fragment here. We basically try to generate the other side of the molecule so that it can have a better activity, right? So we managed to synthesize two molecules. So we only tested two in this case, and we found one of them, the other one that's not working, so that's why I didn't show, but one of them showed particularly good potency against the bacteria with good selectivity, improved selectivity from 2 to 64, which is pretty remarkable. And we also tested this molecule against several resistant or mutated strains of this bacteria, the gonorrhea, right? And we tested about, I think, about 10, mutated strains from the CDC, FDA isolate bank, and we found that it can kill. For some of the resistant strains, it actually works a little bit worse, but for these pan-resistant bacteria strains, this molecule actually works pretty well. And we also tested this molecule in mice models. We basically infected the mice with the gonorrhea, and we tried putting the negative control, which is doing nothing, putting our compound, and also a positive control, which is kind of the first line antibiotic for gonorrhea. And we compared what's the so y-axis is the kind of the level of infection, and you can see that the compound one that we designed can significantly decrease. This is log scale, so it reduces the infection by about 100-fold-ish, right? So that kind of shows that our compound is it also works in vivo. We also went more ambitious, tried to do this purely de novo rather than just try to optimize some initial hits, right? Because it's much harder to start from design something from scratch than something that already has some activity, right? So initially we didn't really thought that it would work, but during the sort of the rebuttal of our work, some reviewer requested that we should go to demonstrate, in order to demonstrate that this method really works, we should do purely de novo. So we just went for it, and we basically generated using this generated model. We didn't even try reinforcement learning here. We just tried to generate about like 100 million molecules, and we just let the property predictor to select the best ones. We selected about 24 compounds. We ordered them, and we synthesized them to test. And we found 6 of them actually had various degrees of activity. And the best one, called DN1, which happened to be actually the simplest design out of the 24, had a selectivity index about 64 as well, right? So it can kill. In this case, we switched to a different bacteria called MRSA, which is a known strain that resistant to a standard antibiotic for this bacteria. And so we can see that this compound can work for this resistant strains pretty well. We again did similar thing using animal models, and we can show that it reduces the infection level as well. Okay, so that's kind of the summary of the results. Just try to show whether this thing actually works in the lab, right? Rather than just something in silico. So let's now talk about the approach behind the scenes, right? Like what's of course, I believe there are many methods that can make this work, right? But we chose a particular type of method that tries to generate molecules as graphs, and I will explain a little bit why we choose this route, right? So just to kind of go a bit more, I shouldn't say mathematical, but try to formulate the problem a little bit more clearly. We have this molecule that can be represented as a graph, right? So each atom is a node, and each bond is an edge in this graph, right? So of course, generating graph, when I first started working on this problem, almost like 5 or maybe 8 years ago, there wasn't much like method developed for for graphs, right? So what people typically do is to convert this into a kind of a string, and then just try to generate molecules as the sequence, right? So there has been a numerous number of work try to do that. But the reason why I didn't choose this route is because the small string doesn't really preserve some of the properties that we care about. So for example, if you have two similar graphs, so in this case, you have two molecules that differ by one bound, right? But because of this, how smiles kind of tokenize or like linearize this graph, because of the arbitrary nature of it, it kind of messes up in the small string representation, you don't see the similarity at all, right? So even though this is only a very small change. And you can also see similar thing for the subgraph relationship, right? If I just want to say, I want to expand the molecule by adding more stuff to it, right? It doesn't really work well in the small space, right? You can't just add a bunch of other things behind, right? It doesn't work out of the box. So, and these properties are kind of critical for lead optimization, but I also believe for de novo design as well, right? Because especially for this variational autoencoder type of models, right? We embed these molecules into this latent space. We would definitely want to preserve this similarity in the latent space, right? If you have two molecules that are similar, but they are very dissimilar in the small string, if you embed it into latent space, you can't really preserve this semantic similarity. So we went for try to design models that can just generate molecules or represent molecules as graphs. So this is kind of the motivation behind the development of this model called junction tree variational autoencoder, which kind of tries to mimic how chemists think about a molecule, right? So chemists think about the molecule in terms of fragments, right? And it basically tries to generate, it's an autoregressive model. Of course, now you can try to come up with like diffusion models too as well. But we just went for a simpler approach that just generate a molecule autoregressively by attaching, we have a vocabulary of fragments, and we try to select select a fragment in each step, right? Try to select the fragment from the vocabulary and try to stitch, different things together. And this is kind of how we try to mimic, what chemists think about when they build molecules in their mind, right? And of course, has a lot of fragment-based design has motivations coming from this biochemistry, right? If you look at these protein-ligand interactions, a lot of them involves these, functional group interactions, right? Like this pi interaction. They all involve like functional groups, or AKA fragments. So that's kind of why we went for that. We did some in silico kind of benchmarking study in a different context on some optimizing binding to another target called DRD2, just because back then we had more data for this target, and we basically tried to see if you apply different type of generated models, either working based on smiles or graph or fragments, which model can give you a better capability to do lead optimization, right? And we can show in this case that this JT-VAE model has a much better ability to modify a molecule to improve its activity, right? And that's kind of what we showed in our work earlier. But of course, now we applied it to recently to the antibiotic setting. So of course, feel free to jump in if you have any questions. But that kind of concludes my first part and on the small molecule drug design, where we developed this generated model for molecules and applied it to antibiotics. It's an important problem. If you are interested, happy to chat more and see what we can do together in this space, right? So now let's look another side of the problem, right? I kind of focus more on the generation in the first part of the first vignette of this of today's talk. But of course, there are other two components that are also very important. So in the second component, we'd like to talk about scoring, right? Without a good model to score, to evaluate your design, you are kind of walking in the dark, right? And you just don't know where to go, right? So this scoring model is quite important. So we will talk about this in a different context in protein design, right? And especially binder design, right? And binder design is a critical problem in therapeutics, ranging from small molecules, proteins, or nucleic acids. You care a lot about finding, something that binds or inhibits a target, right? To modulate its function so that you can, block the disease mechanism, right? So there's a lot of interest in designing, different binders for different type of targets, right? There has been, as I mentioned earlier in the introduction of my talk, there's two. I kind of just categorize them into two. Of course, you can name other type of methods as well. But there's like purely diffusion based, where you just generate the backbone structures. There's also like hallucination based, like more like try to do some sort of gradient based optimization to design protein binders. So we'll kind of go through the hallucination-based protein binder design, and this is a framework developed at EPFL called BindCraft, which achieved a lot of success in a variety of targets. And so that really intrigued me, and wanted to study this system further and to see how we can further improve this. And my take of binder design is, I wouldn't say it's orthogonal, but I want to focus on this problem on the scoring, right? So basically, the basic idea behind BindCraft is you have a set of in silico scores, and these scores, we'll talk about them in a bit. These scores like ipTM or PAE, they kind of gives an in silico assessment of how likely your designed binder would bind to your target, right? And basically, assuming that these scores are good, you do this iterative. So this is the workflow of BindCraft, which is also the AlphaFold 2, and you try to do back propagation and try to calculate the gradient of these in silico scores with respect to your binder sequence, and you try to do this iterative gradient ascent, right? If you want to maximize your score, and you can come up with a series of these scores. But one of the main score called ipTM, which happened to be which if you dive this deeper, look at the behavior of this gradient, you can see that actually this gradient is fairly sparse, and that's because there's some sort of max operation behind the ipTM calculation, which made all the gradient, because of the max operation, you can only go through the gradient only go through one of the residues. So this gives you a very sparse gradient that makes you hard to optimize. Ideally, we want to find something that's right to smoother scoring function, something like a free energy score where you can behave more nicely, that can go through this landscape smoothly, right? So that's kind of the motivation behind the development of a new scoring model. And I think this is, if you have a good scoring model, you can plug that into any type of binder design system, not just BindCraft, but anything, right? And I think this is a very important, an interesting problem. And I'm going to talk about what's my view of, not necessarily the only way, but one of my my approach is kind of try to go back to the probabilistic approaches. So if you are familiar with language models, like ChatGPTs, these natural language models, they essentially try to learn it's the maximum likelihood estimation of your text, right? And you want to generate if you want to generate a sentence that looks good, you want to generate something that has high likelihood. So if your sentence has a high likelihood, then most likely it will be a very fluent sentence, right? And similarly, this idea actually translates to protein sequences as well. If you're familiar with protein language models, people have shown that if your sequence have a high likelihood, it tends to give you a good fitness. Fitness means it has it being functional, right? So in the case of like, I kind of extrapolated this hypothesis a little bit further to these protein-protein interactions, where my hypothesis is if you can have a high likelihood of the structure, right? Not the sequence, but the structure, because the interaction involves a lot about shapes. Then you might have good binding, right? So I kind of try to reduce or formulate this binding estimation problem into this likelihood estimation problem, right? So the key idea is how can we estimate the likelihood of a structure, which is not trivial, because if you look at these like a natural language or protein sequence, they are sequence, right? So and we have a pretty good toolkit to learn like likelihood of these sequences. But when it comes to these continuous structures, I think there's still a lot of still need more development to how to design ways to estimate likelihood of these continuous objects, right? Especially coming from diffusion models, which is still not trivial. So the approach that I took is actually quite surprisingly simple, and it doesn't require any retraining of AlphaFold or BindCraft or any of these protein generated models. So basically, if you have, let's just take AlphaFold as an example for now, right? So without retraining, how can we extract likelihood from these protein structure prediction models? So it took me a while to realize this connection, but there was a very kind of a classic paper back in 2020 developed by University of Toronto, David Dumanol's group. They had this very interesting paper called your classifier is secretly an energy-based model. And this is a figure copied from their paper. They basically show that if you have a classifier, right? Let's say it's an image classifier, you have a neural net. Doesn't matter what kind of neural net, as long as it's a classifier, and you have a softmax operation that try to give the probability of each class, right? And what they showed is that if you ignore the softmax, if you take the logits before the softmax, you can actually get a log likelihood of your input object. So so this is called what they call the joint energy modeling framework. Basically, they observe that this normalizing constant, this is the softmax operation, right? The normalizing constant, actually, you can actually do some math, and you can reformulate this as you can basically calculate, use these logits to define a joint distribution P, X, and Y. X is the input and Y is your class, right? And you just need, here is normalizing across Y, but if you choose to normalize across X, then you can basically get the log PS equals to log sum EXP of the sum of all the logits summed over all the classes. And of course, you have some constant behind. So in the case of and this is already useful, because even though we cannot get a exact log likelihood, a normalized log likelihood, when you compare, given the same target, you can still compare different binders by just looking at this unnormalized log likelihood. So that's what we did, right? So we just need to look for a classifier in your protein folding model. And there are many classifiers in between, but one of the most relevant to us is the confidence hat, where you derive your PAE or ipTM scores. But instead of running through the softmax, right, you just go take the logits before softmax and plug in log sum EXP, and then you can actually get your log P structure, a normalized version of log P structure. And so this is how we calculate the energy from AlphaFold, right? And you just get this out of the box. And we just need to do one more small tweak, because not all PAE being is equal. So here we are trying to predict this error term called predicted align error. And the higher error means worse binding. So we just need to follow how they calculate pTM or ipTM score. We also apply the same TM weighting for the beans and just get this energy what we call pTMEnergy. By weighting different beans, by adding this pTM weighting to the different PAE beans. And then you get your energy score, which we will show later that this is much smoother than the ipTM score. So, but first of all, we just wanted to see if this score is actually a good binding indicator or not, right? So we took, we tried to benchmark it across 14 mini protein binder screens from 2 papers that prior work that did this binder design, right? So they ran like a fish or display system, try to screen different designs, and they accumulated about over 1 million sequences, and a lot of them are non-binders. So we just we subsampled the data set to 1 to 100 positive negative ratio, and we evaluated what's the ability of different scoring models. And we looked at, we found that this energy-based model can give a much higher accuracy than a standard ipTM score, especially when you look at the precision at top 5 or top 10, you can substantially increase this average across targets. So average across all the 14 targets, right? And you can see that precision at top K is much better than ipTM. This is the score distribution of the pTMEnergy across 8 different targets. And the red line indicates the actual true binders. And you can see, of course, it doesn't work for 1 or 2 of the targets, but for most of them, you can see the binders that are enriched at the top, right? This is kind of the distribution of the pTMEnergy, right? Of course, pTMEnergy by itself is the lower the better. So when we plot this plot, we took the negative of it so that it matches your intuition. But in practice, it's always the lower the better. Okay. So we also plugged this into protein RNA binding, right? We took some RNA aptamer screen from this paper in 2012, and we found that this ipTM score, our pTMEnergy score gives much better accuracy as well in the case of protein nucleic acid interaction. So as I mentioned before, right? So now if we have this energy score, we can also plug that into this design system, right? So instead of backpropagating through ipTM, you can backpropagate through this pTMEnergy. And now you can see that if you analyze the gradient of the pTMEnergy with respect to your binder sequence, you can see that this is much smoother, right? It has more information in each update, right? Instead of just having update for one of the residues. And we found this is actually very helpful for improving the in silico success rate of binder design, right? So just so that, just in order to be fair, right? When we evaluate whether the design is good, we still use the ipTM as a way to measure. So we are optimizing pTMEnergy, but just so that we are fair, for fair comparison, we still use ipTM as a kind of a test time ground truth, right? The surrogate for evaluating different binders. But even if with this mismatch, right? Even though we are not optimizing ipTM directly, you can see that with this smoother energy score, you can get much higher in silico success compared to BindCraft, and that uses ipTM, right? So this is not saying that this is just saying that with the same framework, BindCraft is already a very, very good framework. But if we can improve the scoring model more, then we can further improve this system that is already very promising, right? And we also show that with this energy model, you can reduce surprisingly, you can also reduce the clashes of the things coming out of BindCraft. So this does show that if you just put more effort into the designing a better scoring model, you can actually further improve the design system that are already showing very promising results. So that kind of concludes the second part of my talk. And let's kind of, for the sake of time, let's go to the third part of my talk, that is less on the machine learning, but more about how to build a system that can be purely autonomous, right? If you look at all the previous, like the antibiotic design workflow, or these protein binder design workflow, we typically try to finish our job by one round of design, right? We don't want to go for multiple rounds. So, but if you do this way, of course, it's simpler, but it means the model cannot learn from the new experimental results, right? And even if, we kind of measure the success or the performance of different models by just looking at the success rate of the first round. But of course, from the experimental design perspective, it doesn't mean it's purely exploitation, right? And there's no exploration whatsoever. So if you want to think about, this design problem, right? Maybe it's okay in the beginning, we just pay more price by explore some different areas and try to improve your scoring model a bit more, right? So that later on to try to exploit, right? So we currently, with the previous systems, we are not leveraging any exploration. And of course, that's because experimental testing is actually the bottleneck, right? It's expensive to order small molecules or synthesize these proteins. That's why we try to finish everything in one round, right? So in this case, if we can build something that's more autonomous, that can reduce the manual labor of experimental testing, then we can try to build this fully closed loop system, right? And also I mentioned that the selection of the candidate molecule is purely greedy, right? There's no exploration whatsoever. So that's kind of the motivation behind the development of this autonomous lab system, which we demonstrated in the case of small molecules. So we haven't yet done this on proteins, but basically this is a joint effort with a lot of chemical engineers at MIT. So we published this work in Science 2 years ago, but we're still tweaking the system. It's just a very it's a pretty big system that still needs to be improved. My role in this project is more on the generated modeling part, which I kind of already talked about in the first part. And basically, this has the generated model that can generate things, and then we have an automated lab that can synthesize these molecules, and then we can test these molecules and then loop it back, right? Loop the new data, feed that new model, new data to the property prediction model and the generated model. Right, this is kind of the robotic system that my collaborators built, which allows us to quickly iterate through different molecular structures. We applied this. I wanted to apply this to antibiotics, but back then we were working on this DARPA project, which specifically requested to design of molecular dyes. And these dyes, basically, they're molecules that has colors, right? So, these are different wavelengths of different molecules, and depending on the different wavelengths, absorption wavelengths, different molecules can show different colors. And this is quite important, not just for beauty of your hair, but also for different biological experiments, right? Especially imaging, right? So if you can design nice fluorescence tags for different proteins or different biomarkers, you can improve your diagnosis or just imaging experiments. So just trying to say that this molecular dye design problem is quite relevant in the context of biology, right? So in this case, we look at 3 different properties, right? The wavelength, right, which is the color. We also look for the kind of the solubility, right? We don't want the dye to kind of dissolved in when it comes to water. Or we also want it to be photostable, right? So we don't want to degrade quickly, right? So we try to aim for designing molecules with 3 properties in mind, right? And I think, of course, I talked about the generated model already. So I just want to touch base on how do we do this loop, right? Basically, what molecules shall we synthesize and test, right? So in this case, we no longer just go for greedy, right? We want this balanced exploration trade-off, right? So in order to do that, we need to quantify the uncertainty of a prediction. And here we actually just went for something rather simple. And I'm pretty sure there are better ways to do this. We just train different model ensembles and look at the ensemble variance as a way to quantify uncertainty, right? If you have a compound, if you go through 3 different models and each of them give you very different predictions, then probably this is something that you want to test, right? That you want to test and use that data point to improve your model, right? That's kind of the idea behind this. And of course, the other thing that we need to take care of is we need to balance the exploitation and synthesizability, right? You might have a molecule that is really hard to synthesize, and that's probably not something that we want to explore, right? So here we, my colleagues developed this, ritual synthesis platform that can kind of in silico, like come up with a route of a synthesis route that can, starting from these purchasable compounds through a series of reactions, try to make the final molecule, right? And we can use this as a kind of recipe, right? Basically come up with a recipe to cook this molecule automatically in the robotic system, right? So we want to design molecules that we can cook in our kitchen, right? So that's kind of the idea. And we basically always select the top regions where it's both valuable, right, and also synthesizable, right? So that's how we that's another factor in the selection of molecules to test. So basically, we used this uncertainty estimation and the synthesizability estimation, and we use that to do this multiple rounds of designs, right? And in the case of molecular dyes, we started from 4 different scaffolds and tried to build molecules within each family. And so and you can see on the left-hand side, this is the mean absolute error of your property prediction model. And initially, we don't really have much data to measure the wavelength or the solubility or the stability. So initially, it was pretty bad, right? Each dot corresponds to each of the scaffold family. And you can see with different rounds, across multiple rounds of this experimental design, you can improve the performance quite a bit, right? To almost experimental error, right? This is the red line is the experimental error, right? So that's kind of what we achieved, right? So this is one of more like visible plot of if we add across one round, if we add like on 200 data points. No, I think this is across 4 rounds. We added around like 200 some data points, and you can see that the correlation between the prediction and the experimental measurement gets much better. Oh, shoot. Sorry, I stepped on it. Thankfully, my talk is almost done, so let me just unplug and see if. Can you come and help me a bit?
Yes.
Coming? Cool. All right. I should not step on this. Cool. Yeah. So yeah, we also did an exploitation study where we tried to just find molecule with high wavelength. We want certain color. We want this try to not be dissolved and try to be stable, right? And we took we defined the molecular value in terms of all the property values and divided by the ensemble. This is the variance, but we actually took the 1 over the variance, so that it the lower the more that we should exploit, right? And plus the 1 divided by the cost, right? So we we designed 4 molecules with high molecular value, right? This is across multiple rounds. The color shows the molecular value, and we selected some of the best ones to test. And we can show that in the case of wavelength, the prediction versus the experiment results kind of match closely, right? So for the solubility, is something that surprisingly it didn't go very well in terms of the agreement. There's like 2 units away, but for wavelength and for the stability, actually, it's pretty good. So that's kind of what we did, but everything is automatic in this. You just need a human operator to just press a bunch of buttons to do this. So it's pretty cool. And I think now we are talking about plugging this into a kind of a small molecule kind of a target find something that can bind to a target, try to adapt this system. Okay, so that's kind of the summary of my talk today. We kind of talk about 3 different challenges, right? Like how to generate new like graphs, how to come up with good better scores to evaluate these designs, and also how to close the loop by bringing this autonomous component to it to accelerate the experimental part. And basically try to combine these, algorithmic innovation, we can show real world impact, right? Especially in the antibiotic case, I think it's pretty cool. So yeah, would like to thank my collaborators. They put, my work is about 2 weeks. They took a year to do the study of these animal models. It's pretty impressive. Of course, autonomous lab also took a lot of labors. But I think we are doing something really cool in this space, and happy to see if you have any questions. But I want to thank all these funding agencies for their support as well. Thank you so much.